distort this again. Do an NCl3. So trigonal pyramidal with CL-NCl angle of 109.5. That's going to be set by the EPG of tetrahedral, 109.5. However, do lone pairs take up more space or less space than single bonds? They take up more space, so that's going to push these three in the pyramid in towards each other, compress it. This needs more space, it pushes these three in, which is going to distort. Each lone pair distorts the angle by about 2 degrees. And so what we're going to say is this could be distorted to 107.5 degrees distorted angle. It's just a guesstimate, but that's kind of what we might expect there. There are 2 reasons I don't like their drawing. What's that? Yeah. Reason number 1, there's no lone pairs. I don't like that. And then reason number 2 I don't like it is,
they have the wedge and dash mixed up.
yeah, the wedge and dash, you get see they're flipped like that? I don't see, unless I'm looking up, you know, but I don't want to be, I want to be looking down at it. Because the wedge and dash are the wrong positions. Now if I'm looking down at this is coming out, and that one's going in. And so don't copy this drawing. Even though this is what the book has, don't copy this. It's not a very good drawing. Let's take a look at this. We'll just analyze this one. Okay, if I look at this carbon, how many groups of electrons around this carbon? This is the first thing we do. Count how many. Some people say 4. They say 4 because it's a single bond, and a double bond counts as 2 groups. Does a double bond count as 2 separate groups or 1 single group? It counts as 1 single group. We can't split the double bond into 2. We've got to take it as 1 double bond. And so there are 3 groups, single bond, and double bond. If there are 3 groups, what's its EPG? Trigonal planar, in this case. This is a trigonal planar. So everything's flat, and there's 120-degree angles. If I look at the geometry of the bonded atoms are also trigonal planar. And so this carbon should be trigonal planar. Well, this is the same. This carbon is trigonal planar, and the angle, the FCC angle is 120. In fact, all the angles should be 120. But which one takes up more space, a single bond or a double bond? A double bond. And so a double bond is kind of like a lone pair. It's going to take up more space. If it takes up more space, it's going to push this fluorine back. If it pushes this fluorine back, then it's going to widen this angle by about 2 degrees. And so we expect the FCC angle to be about 122. And then this FCC angle should be about 122. So if this is 122, this is 122, then all these angles have to add up to 360 because they're in the plane, the same plane. So that means this angle gets compressed to 116. A plus 2 degree here, plus 2 degree means minus 4 degree here. And so the FCF angle gets reduced to 116. So distorted angles, 116, 122, 122. Does that make sense? The undistorted, they're all 120. Now, how accurate is that? Well, these are just guesstimates on the angles, but this looks trigonal planar. Some distorted angles. All right, the next thing, we're going to come back to shapes again. But Before we do that, I want to talk about polarity. Like for example, this nitrogen trichloride is a polar molecule. If I look at nitrogen trichloride, look at the nitrogen chlorine bond. Is this what type of bond is this nitrogen chlorine bond? What type of bond is that? Is it an ionic bond? Yeah, it's a covalent bond. Is it a non-polar or a polar covalent bond? What do you expect? It's a polar covalent. Which one's more electronegative, chlorine or nitrogen? Actually, this is tricky. This is a bit tricky. Maybe I shouldn't do this one. Actually, when you look at the electronegativity difference between nitrogen and chlorine, it looks as if chlorine is, yeah, pretty close. There's not much difference, 0.2. It's borderline non-polar. This wasn't a good example. And there's one more trick to using these. It's often stated that the three most electronegative elements are fluorine, oxygen, and nitrogen. But if you look at it, look at nitrogen's tied with bromine, chlorine's tied. Well, chlorine's actually more. And there's one other thing that impacts the behavior of this, and that's the size. If we had bromine and nitrogen, we'd say they're tied, but it turns out nitrogen's going to be the winner. Why would nitrogen be the winner? It's because of its smaller size, which makes it more. So these numbers are a little bit tricky in the sense that there's additional things that you have to know, but we're not going to get into it just yet. Okay, now, this wasn't a good molecule. Let's pick an easier molecule to deal with. And so this is one that we need some more data to do, but it's fairly non-polar bonds. This one's a lot easier. This is methane. We do methane. We just drew the structure of methane. CH4. If you look at methane, tetrahedral, 4 carbon hydrogen bonds. How would you characterize these bonds here? These bonds would be characterized as non-polar covalent bonds. We'll just say non-polar bonds here. Versus carbon tetrachloride. Carbon tetrachloride, there's definitely going to be a difference in electronegativity here because carbon's at 2.6 and chlorine's at 3.2, so there's going to be a difference. Chlorine's more electronegative. And so carbon tetrachloride is going to be a tetrahedral molecule, shaped molecule like this, with 4 chlorines bonded. Now, this is going to have polar bonds, and so what it means to have a polar bond is that the electron cloud is going to be distorted. Over here, if I look at the electron cloud is pretty symmetric. That is, both hydrogen and carbon have about equal pole. Carbon's slightly more, so it's slightly polarized towards carbon. Essentially, it's pretty even, the distribution. Well, this is kind of a fair sharing of electron cloud, and so nobody really comes out short, nobody really comes out ahead. But when we look at chlorine and carbon over here, then it's not very fair, the sharing of electron cloud. In fact, chlorine takes most of the electron cloud. If chlorine takes most of the electron cloud, what that means is that there's more electron density around chlorine. If there's more electron density around chlorine, then chlorine's going to build up a negative charge from having all that negative charge density around it. And carbon's going to come out short. And so this is what we call a polar bond. And we can show polar bonds by showing these deltas. Delta minus, delta plus. Delta minus means we're building up negative charge here. And delta plus means we're building up positive charge down here due to this distortion electron cloud. Whereas the delta plus and delta minus here are negligible. There's really no what we call a bond dipole. This is a bond dipole. There's another way of showing this bond dipole, and that's by drawing like a vector arrow. We draw this arrow that's pointed towards the more electronegative with a positive tail. And so this green arrow and these red delta minus, delta plus show the same thing. So we don't have to write both of them there. Normally we just write this arrow here, but it doesn't matter either way, we can represent that. And so this is a polar bond here. And so we definitely have polar bonds. So for example, we'll have a polar bond here, here, this wedge coming out, and here, this dash going in. And so we got 4 polar bonds. And so does that make this molecule polar? Now molecular polarity, we look at it as adding up all the bond dipoles. In other words, this is like a tug-of-war. If there's a tug-of-war here, chlorine's winning. If there's a tug-of-war here, chlorine's winning. Tug-of-war here, chlorine's winning. However, what we do for a molecular dipole or molecular polarity is we add up all the tug-of-wars. So these tug-of-wars are happening simultaneously, and then we see how they add up. And so, you know, one is pulling straight up, and one is pulling off to the right. Well, if we only had one tug-of-war going on, like this top one here, then the molecule is being pulled up. Now, if we have 2 of them, like this top one here, and this one to the right, then the molecule is going to be pulled this way. You see, if this one's pulling up and this one's pulling down this way, the net is going to be this way. That's how they add up. And so what we do for molecular dipole is this. Molecular polarity or dipole is we sum up all of the bond dipoles in 3 dimensions. In other words, we look at all the tug wars going on in 3D and see which way it goes. And so there's going to be one more dipole sticking out forward, and then one more dipole going in like this. And so I have 4 dipoles. Now, when I think about the tetrahedral, you know, this is what we call spherical symmetry. Like say you're stuck inside of one of those rolling spheres, you know? If you're stuck inside of one of those rolling spheres, how do you want to orient it so you don't start spinning? How do you want to orient your body position? And so if you're stuck inside of the sphere, what you might want to do is you might want to put 1 foot forward and maybe 1 foot back. You know, and then how do you want your arms? So maybe this doesn't look so great, but like 1 foot forward, 1 foot back, and then how do you want to put both arms up like this, or maybe both arms out like this? Yeah, maybe like that. And so what you might want to do is you might want to do something like this, where you put one arm, and so it might be something like this, where this one wedges out, this one goes in. So it's like a tetrahedral type arrangement. And that would be kind of balanced there, this tetrahedral arrangement in the sphere. And so that's why we say tetrahedral geometry is spherically symmetric. It's spherically symmetric. And so what happens is if there's a 4-way tug-of-war like this, then no side wins. What happens is when we sum up the bond dipoles here, they sum up to 0. The sum of the bond dipoles equals 0. And so it's essentially it's equal and opposite in 3 dimensions. Here, when we sum up the bond dipoles in methane, they're going to be equal to 0 because there are no bond dipoles. I mean, the bond dipoles are close to 0. They're negligible. And so we treat the bond dipoles as 0. And so this gives us a rule. All hydrocarbons, no matter how complex the shape is, you know, the shape can be complex. When we look at the bond dipoles, they're all going to be 0. So we might think isobutane, you know, if we had a tug of war with isobutane, is Is it going to cancel out? It doesn't look like it's going to cancel out, but it does because there's no tug of war. There's no individual tug of wars. And the same thing, isopentane. Isopentane doesn't look like it's going to cancel out, but there are no bond dipoles. There's no tug of war. So all hydrocarbons are non-polar. That is, they have no bond dipole. Versus something like this, an alcohol. Alcohols are very polar because there are bond dipoles here. You know, oxygen's more electronegative, so there's a bond dipole here, bond dipole here. It's going to be pulling up. Methyl is very non-polar. This is called methyl group. Here. Over here, you know, this is called butyl group, but this alcohol is very polar, whereas this butyl group is very non-polar. That has an impact on its physical properties. So for example, methanol is very soluble in water, but did you know butanol is not? Butanol doesn't really dissolve in water. Methanol does. And that's because butanol is more oil-like. Oils are non-polar than water-like. You know, the hydroxyl group here in alcohols is very water-like. And so this is similar to water, but the hydrocarbon part is similar to oils. So let's look at some other structures here and see. CO2 has very polar bonds. I can see the bond dipoles here. You know, oxygen is more electronegative, so it's pulling the electron cloud towards it, building up negative charge. As electron cloud gets pulled away from carbon, it's building up positive charge on carbon. The same thing here. And so there's a tug of war pulling left, a tug of war pulling right with the bonds. But what's happening with the molecule as a whole? What's happening with the molecule is that the bond dipoles are equal and opposite, and so they cancel each other out. And that makes CO2 polar or non-polar. It makes it non-polar. So CO2 and water, CO2 is not very soluble in water. CO2 is more soluble in like oil than water. But if you look at water, you know, there's a bond dipole pulling up this way, a bond dipole pulling up this way. So if you add up these two, which direction will water go? So if it's pulling this way and pulling this way, it's going to pull net straight up. And so this is the net dipole, or the molecular dipole. And so what we see here is this is a polar molecule. However, this is non-polar. And so water and CO2 are different in terms of polarity. Well, this is carbon tetrachloride. Carbon tetrachloride is non-polar. We have these 4 bond dipoles, but in a tetrahedral arrangement, we have spherical symmetry that cancel each other out. This is called chloroform, or CHCl3, trichloromethane. When we look at that, now we have a hydrogen here. Well, hydrogen-carbon bond is non-polar, so we have 3 polar bonds here, here, and here. And the delta plus belongs to that carbon. And so there's going to be a net pulling here, pulling here, and pulling here. So the net, when you add it up, pulls out this way. Here. So this is polar. CHCl2, non-polar, non-polar. This is a polar here. This is a bit tricky, but here, let me redraw CHCl2 since that drawing hard to figure. CHCl2 is going to be tetrahedral. And so we'll put the 2 chlorines in the plane like this. That means a hydrogen is going to wedge out and a hydrogen is going to wedge in, out or dash in. Carbon-hydrogen bonds are non-polar. Carbon-chlorine bonds are polar. So we're going to have a bond dipole. If we had one bond dipole pulling up, we'll have a net pulling up, or a molecular dipole pulling up. But we have one pulling up and one pulling down into the right. And so the net movement here is, the net molecular dipole is, we add up these 2 and we get a net molecular dipole like this. So it's going out that way. And so dichloromethane is polar. If you look at chloromethane, chloromethane is polar too. We have these three hydrogens here, non-polar. We got the chlorine up here that's polar, so the net is going to match the bond. And so the bond dipole and the net dipole are exactly the same in chloromethane. So chloromethane looks like this. We'll throw the chlorine on the top here. And the three hydrogens down here. And so the bond dipoles like this. There are no bond dipoles in the carbon-hydrogen, or negligible. We'll just say negligible bond dipoles. And therefore, the molecular dipole is the same as the bond dipole. The same thing. When we go to methane here, methane's again, methane is although they show the bond dipoles here, they're negligible, they're small. Here they're saying the bond dipoles cancel each other out, which is true. But even when you have the bond dipoles not canceling each other out, like here, even when the bond dipoles don't all cancel each other out, it's still nonpolar. They wouldn't cancel each other out. This one they cancel each other out here because it's very spherically symmetric. Did I talk about these organics? Did we do carboxylic acid? Yeah. Did I have you draw acetic acid? No? I'm going to have you do some drawings. Actually, the first drawing I'm going to have you do is, let's do, this is methanol, this is butanol. Let's draw ethanol. I'll just draw it first for you guys. So, if I draw ethanol, first we draw the Lewis structure. Like this. And then we'll look at it here. First we'll look at the first carbon here. Actually, this is the second carbon. You know how we number the carbons?